till the tyndall effect, so I assume it is only till the mixtures and not the pure substances are not there. Yes. I'm opening the NCERT here, just a second.
What, ma'am?
I'm opening the NCERT here, but just a second. Yes. Could you see that? Is it visible?
Yes, ma'am. It's visible.
Fine. Yes. So Mithun, quickly tell me. I'm asking you all the topics. So basically, the mixture is your main topic, I think, in tomorrow's test. Yes. And then till here, till this part, till the colloid. Respond, beta. Yes. Yes. Fine. So then we'll just take the NCERT and we'll start revising from the NCERT itself. If there's any problem in that you want me to explain in detail, please do let me know of that. Okay. Fine. Yes. Are both of you ready? We are starting with the second chapter. Just a very quick revision here of the basic concept which is involved in this chapter, that is matter. When we talk about matter, okay, we know that the matter has some chemical composition. Chemical composition means what? How is the matter made of, right? What is the manner in which the matter is made of, right? So we have the chemical composition. And we know that one particle is there, one particle is really small. Therefore, when we see the matter around us, there are many particles which are combined together to give us that matter. This is the basic point here. Now, the point is, if the same type of particles have combined together, same type of particles I'm using, okay, then that's a pure matter. Then that's a pure matter. If different types of particles have combined together, okay, something like this, then it's an what kind of matter? Impure matter, right? Now we are just specifically focusing on impure matter as of now. What is it that the impure matter is called as? That is called as a mixture. What is it that is called as? Mixture. If I'm saying what mixture, I'm referring to a matter which has different types of particles in it. That's the only point here. If I'm referring to a mixture, I am saying that the matter has different types of particles in its composition. Is this point clear to both of you? Fine. Now, see, mixtures further. Okay, let's quickly understand. Let's say I have this particle, okay, and I call this as A. I have these particles, something like this, okay, and I call these particles as B. Yeah. I have mixed both of them. I have mixed, because see, here you can see that this is a pure substance because the same kind of particles are there. This is again a pure substance because same kind of particles are there. What I'm doing here is that I'm mixing two or more than two pure substances. Two or more than two pure matter. If I'm mixing, what am I getting? I'm getting impure matter, or rather a mixture. Mithun, Dima, both of you say yes or no.
Yes, ma'am.
Yes. Fine. Mithun, is it okay to you? Okay, you're not responding much. Do you have any problem in the mic? No. What has happened to you? Are you just going to talk using the sign language?
No.
Okay,
No.
fine. Okay, fine. Fine. No worries. Okay. So that is a simple point of mixture. How do I define mixture? When two, okay, or more than two. What kind of substances? Pure or impure?
Mixture is impure.
It's impure.
Pure substances combined together, combined or mixed together, we get a mixture. Is this point clear?
Yes, ma'am.
Fine. What are some of the characteristics of a mixture? Is the composition variable or is it fixed?
Their composition, like, it's not fixed.
Wonderful. So we have a variable composition. Variable composition simply means the amount of the substance A and the B, which are in themselves they are pure, but when they are getting mixed, the variation could be there, right? Let's say we had 50% in the first case. In the second case, I just take 30 and 70 ratio. The variation is there. The composition is variable. Fine. The second point: what kind of bonding is there between the two substances? What kind of bonding is there between the components of the mixture? You understand
Heterogeneous
bonding?
and homogeneous.
Sorry,
Heterogeneous and homogeneous.
I'm just talking about a mixture.
It mixes together well.
Fine. But my point is, let's say we have two types of bonding, right? Either the physical bonding could be there or the chemical bonding could be there. So always remember, whenever there is a variable composition, okay, whenever there is a variable composition, that means the physical bonding is there and no chemical bonding. Is it clear? And whenever chemical bonding is not present, it's a mixture. It's an impure substance. Whenever chemical bonding is present, it's a pure substance. So this is the simple point of differentiation here. Therefore,
Okay.
that is why we say that when two or more than two pure substances are combined or mixed, the combination is a physical mixture. That therefore we get two different components in it. Is it clear? Physically bonded. Very important. Next point, very important. Let's say I had two components of this mixture, A and B. A was a pure substance, B was a pure substance, right? The properties of this mixture A would be a result of what? Would that be a mixture of the properties of A and B, or would that be completely different properties from that of A and B?
It will be the properties of A and B.
Wonderful. Therefore, properties are a result of properties of constituting, okay, components. Is this point fine? Wonderful.
Yes.
Can you quickly give me one example for this third point? For all of these points, can you give me some examples of a mixture? Yes,
Copper sulfate with iron.
copper sulfate with iron. What will be the point there? How can you prove that it's a mixture? Some day-to-day life example that you see
And
in
sugar
day-to-day
and
life.
water, sugar and water, salt and water.
Sugar and water. Fine. You are saying sugar and water. So
And
can I assume that sugar
water,
is a pure substance on its own? Water is a pure substance on its own. We are mixing both of them, and the kind of bonding that which is taking place is not chemical. Rather, it's a just a
Yes.
mixing, that's physical bonding. Fine. Now the composition can be varied in case of sugar and water.
what ma'am?
Can the composition be varied in case of sugar and water?
Um,
Can I add,
no.
like, let's say you are making sugar and water solution, I'm making a sugar and water mixture, right? I can add more sugar than you, or you can add less sugar than me. Yes, that is possible. So that is what do we mean
Yes.
by the variable composition. Fine.
Mhm.
The properties of that mixture will be what? Will that be just sweet, or will that be liquid and sweet? A mixture of the properties of the constituting component. Is this
Mhm.
example clear? Fine. Any other example? Quickly, very quickly. Hmm. Fine.
Ma'am?
So we have, yes. Can I say that I take two powders together? I take simple, let's say I take orange powder and I take red
Mhm.
powder and I mix them together. Can that be a
Mhm.
can that be called as a mixture?
Yes.
Yes. Can I have a variable composition in this? You might add some, like, let's say 60 grams of the red powder and I just add 2 grams of the red powder. Yes. The
Mhm.
composition is variable. Fine. Yes,
Variable.
Mithun, you were saying something. Please go ahead.
You are
You were
asking
saying
the
something.
examples of the mixtures, right? That's what.
Yeah, fine. So we are going to discuss that one by one in the different types of solutions and mixtures that we are going to study. Okay. Okay. Now mixture further are divided into two types: homogeneous and heterogeneous. See, homo means same. Homo means
Same.
same. Hetero means different.
Mhm.
Okay. So let's say we are mixing two substances. Let's just take the case of two substances being mixed together. Okay. When if they are mixed uniformly, if the composition is uniform, as in the mixing is uniform, the even distribution has taken place between the two components which have been mixed, then that means the mixture will be a homogeneous mixture. Therefore, uniform composition or basically even distribution. Okay. Okay. Whereas in case of heterogeneous, will there be even distribution or will that be uneven distribution?
Uneven distribution.
Uneven distribution. Clear? Fine. The next point. Can you give me an example of a homogeneous mixture that we have just now based on the properties? Mithun, yes, beta, please respond.
Yes, ma'am.
Any example of a homogeneous mixture, beta, which will have an even distribution all throughout the mixture?
Mm,
Any example? Actually, let's take this example that you just now told me of sugar or water. Is that a
and that is not
homogeneous mix?
homogeneous, right?
That is
That is not homogeneous, right?
fine. That's what I'm saying. Let's try to understand that. Let's say you have mixed properly sugar and water. Fine, properly mixed. After proper mixing, I'm not saying you have left that in between. It has been mixed properly. Now, will every sip give you the same taste? Will every sip give you the same taste, or will that be different? After it has been mixed properly, then my point is that. Yes. Yes, bachcho. Dima, respond, beta.
Ma'am, one is half liter of milk and half liter of water.
Half liter of milk and half liter of
Water.
water. We mix it. Then you are saying whether that will be homogeneous or heterogeneous.
That will be homogeneous.
That will be homogeneous. It will appear to be homogeneous. The point is that's the thing. It will appear to be homogeneous. It will not be homogeneous. Then we'll understand why. Fine. Coming on to the next point. First, we are going to discuss homogeneous in detail. Okay. What is it that the homogeneous mixture is called as? What is it that the homogeneous mixture is called as? Yes, Mithun beta.
It's
Solution.
like the same substances.
Solution. Homogeneous mixture is referred to as a solution. Clear? Homogeneous mixture is referred to as a solution. Now, the solution will have two components here. One will be the solute. The other will be, Mithun respond, the other will be
Solvent.
solvent. Okay. Together, they will make the solution. Is this point clear till here?
Yes,
Fine.
ma'am.
Now, see one point, very important. Important point here regarding the alloy. Okay. See, the solution could also be solid, liquid, gaseous. That is not the point here. Solution could be solid also, solution could be liquid also, solution could be gaseous also. Let's take the example of a gaseous solution first. So liquid, you just now told me that is, let's say I'm taking sugar in water or salt in water. Clear? That is a liquid one. Tell me one example of a gaseous solution.
H2O.
H2O and gaseous solution.
Oxygen and carbon dioxide.
Sorry, oxygen and, wonderful, oxygen and
Carbon dioxide.
so basically, can I say air is nothing but a mixture of different gases present in it? Therefore, the solution is a gaseous solution. Yes or no? Yes,
Yes,
it's a
ma'am.
gaseous solution. So therefore, air is an example of a gaseous solution. Fine.
Ma'am,
Coming
but
to the
every gases are not mixtures, right?
every
Every gases are not mixtures, right?
the gases are not mixtures. I am saying oxygen is a pure substance, nitrogen is a pure substance, carbon dioxide is a pure substance. We have mixed them together. This has resulted in the formation of a mixture which is homogeneous in nature. Which is homogeneous in nature. Is that clear, Mithun? Huh?
Yes, ma'am.
Yes. Fine. Now coming to the solid solution. Give me one example of a solid solution very quick.
Salt and sugar.
What's the state of the solution? Is that liquid or is that solid? That is solid. Okay. Oh, sorry, that is liquid. Salt and sugar,
Ma'am,
that is liquid. Yes, yes, Mithun.
the salt and sugar is heterogeneous, right?
We will see that why and how. Okay, we will see that. No worries. Okay. Yes, solid solution. But very quickly, solid solution. Acha, lemonade, what is it? Is it homogeneous or is it heterogeneous?
It is homogeneous.
Method
Mm, homogeneous.
homogeneous. Then if lemonade is homogeneous, why are you saying that sugar and water will be heterogeneous?
Because the sugar will dissolve in water and
I am saying when the sugar has dissolved properly, better. That is the point. I am continuously saying that. If that happens, if mixing has been properly taken place, then tell me.
yes, ma'am,
In case of
mixing would
lemonade,
proper.
also we are doing the same process, right? In case of lemonade, what are we doing? We are having water, we are mixing some amount of sugar and salt, and then we are adding lemon, right? That's the only point. Then why do you think that lemonade would be homogeneous, but sugar and water will not be a homogeneous mixture? See, you can clearly discuss that with me, no problem. But you need to explain
Ma'am,
me your
sugar and
point.
water will be homogeneous, right?
Yeah,
It's not.
yeah, that's what I'm saying.
Yeah.
So, but you were saying it should be heterogeneous.
No.
Then what were you saying? Should be heterogeneous.
You said that we said that sugar and water were not homogeneous. Something like that.
No, I've been saying that sugar and water, they are homogeneous. They are not heterogeneous. Yeah? Is the confusion
We were
clear?
ask,
Mhm.
we were
Yes,
asking
Deepak,
about sugar and salt.
sugar and salt mixed together, that is obviously a heterogeneous mixture. Mithun, was that the point? Should we move ahead? Any confusion till here? Should we move ahead? Fine.
Mm.
Solid solution. What is it? Alloys. What are the alloys? Mixture of two or more than two elements. Yes, metals or non-metals. Simple terms.
Mm.
Okay, so you know alloys. I'm not writing the definition here. Now, alloys, see, there are some exceptional points in alloys. Alloys also are a mixture. Okay, they are a mixture. Why are they considered as a mixture? Because they have a variable composition. They have a variable composition. Fine. But there's one point which is very important to be noted. The bonding in case of alloys is chemical bonding. Okay, chemical bond. Let's say, give me one example. Let's say we have what? We have zinc and copper. Okay, bonded together.
Mm-hmm.
Now this is an alloy. Okay, that is brass. Clear? Fine. Now zinc and copper, both of them are elements. Both of them are bonded together. But what is the nature of bonding here? That is chemical bonding. Now, this chemical bonding generally might say that the alloys, because of the presence of the chemical bonding, is a pure substance or is a pure matter. But that is not the case. Why is that not the case? Because in case of alloys, the mixture, the variable composition could be there in the mixture, which is not the case for the pure substances. Are you getting this point?
Yes,
Although
ma'am.
the bonding is chemical, but the main point here is that the variable composition is present. Therefore, alloys are mixtures and not pure substances. Is it clear?
Yes, ma'am.
And they are homogeneous. Let's say we have a sphere of brass. Okay? It's not that at this point we will have more of zinc and at this point we will have less of zinc. It will be homogeneous throughout the mixture. Therefore, alloys are homogeneous mixtures. Therefore, alloys are solutions. What's the state of the solution here? Solid solution. Is this point clear? Any confusion in case of alloys?
No.
No.
Fine. Now, quickly, we are going to discuss some of the properties of solutions. Mind it, at times, solutions might be referred to as true solution. Whenever we are referring to as true solution, we are referring to homogeneous solution. Please be mindful of it. Okay. Properties of true solution. First of all, it is homogeneous. It is homogeneous. Second, is that the size of the particles? What will be the size of the particles here? Always. Mithun, that's the point here. Very important. The size of the particles will be less than, okay, less than 1 nanometer. Is it clear? If the size of the particles is greater than 1 nanometer, it cannot be categorized as solution. Is it understood?
Yes, ma'am.
Fine. And because of this property of the size, which is specific to the case of solutions, the further properties which we are going to study are because of the size. The third is the mixture is stable. What do we mean by the mixture is stable? When the mixture is left undisturbed for some time, the different components will not separate out. That is what do we mean by stable. Yeah. Let's say we have mixed properly sugar and water. Okay, proper solution has been prepared, and we have left that for some time. Will the sugar and water separate out into separate components? Yes or no?
If it's dissolved in the water, no.
No. That's what I'm saying. When it has been dissolved properly, mixed properly. Okay. Mithun, please respond, beta. Will they separate out?
No.
Therefore, can I say that the mixture is stable? Therefore,
Yes, ma'am.
homogeneous mixtures are stable. And why are they stable? Because of the size of the mixture. That is less than 1 nanometer. Clear? Fine.
Yes, ma'am.
The fourth point. Do they show the Tyndall effect? They do not show the Tyndall effect.
They do not show the Tyndall effect.
Yes. What is Tyndall effect?
The in which the light passes through the solution.
Fine. So in simple words, but a Tyndall effect is when particles scatter the light, okay? And because of this scattering by the particles, the path light becomes visible. The path of the light becomes visible. Is it clear? That is Tyndall effect. Path of the light becomes visible. Clear? And the path of the light will only become visible when they have been scattered by the particles. And when will the particles scatter the light? When the size would be, big enough to scatter the light. Are you getting the understand? Are you understanding the concept? The size is very small. Therefore, all other properties of the solutions are there. Fine. Next point, and that is to understand this. That is, in case of homogeneous mixtures, which is solutions, okay, actual dissolving takes place. Actual dissolving takes place. Why am I saying actual dissolving? Because if the particle size is smaller, okay, let's say beta, let's understand this thing. Okay, these are the water molecules. Okay, they have certain space between them because of the presence of intermolecular spaces. Okay, let's say I'm talking about some other particles. Okay, which have very small size. That is why I'm referring them as solutions. Okay, because they are quite smaller, they will actually get intermixed like this. Okay, therefore actual dissolving is taking place here. Had the particles been greater like this, will they mix here properly? Tell me, will they get dissolved? Yes or no? They will not get.
Yes, ma'am.
Fine. Dima and Mithun, clear. Why are the homogeneous mixtures uniform throughout? They have even distribution. Why? Because of the size of the particles, and because of that, we have all other properties of the
No, the mixtures.
of the mixture. That is, in this case, we are talking about solutions or two solutions. Fine. Quickly, I'm opening the NCRT. Open up your NCRTs. Alloys, we have discussed. Okay. Fine. See, a solution has a two components. Okay, solute and solvent already discussed. Fine. So the component which is present in the larger quantity is referred to as
No.
solvent. The component which is present in the larger quantity is referred to as a solvent. Okay. The component of the solution which is present in a smaller quantity is referred to as the
Solute.
solute. Fine. In the case of sugar and water, what could be the solute or what could be the solvent?
Solute is sugar and solvent is water.
Solvent is water.
Fine. Fine. Let's say I'm giving you the case of air. We just now discussed that air is a solution. Yes, that is, it's a homogeneous mixture. What could be the solute and the solvent in case of air? What's the solvent in case of air? Mithun will answer. Mithun, you answer please. Just a second, Dima. Okay.
The gas which is in larger quantity, which
And which is it? It's nitrogen, right?
yes, ma'am.
Nitrogen. Right. So that is the point. All of this has been understood. Quickly come to the examples discussed in the book. Solution of sugar in water is a solid in liquid solution. See, the state of the solute and the solvent could be different, but the state of the solution is generally determined by the state of the solvent. I repeat, the state of the solution is generally determined by the state of the solvent. In case of water and sugar, the solvent is sugar. Therefore, the solution will come out to be liquid because the solvent is liquid. Are you getting this? Fine. So see. In this solution, sugar is the solute and water is the solvent, already discussed. Come to this point. Solution of iodine in alcohol is known as tincture of iodine. Tincture refers to alcohol. So some amount of iodine is mixed in the alcohol. Now alcohol is liquid, iodine is solid. But overall, the state will be of this solution will be what? Liquid. Yeah. What is tincture of iodine? Is it a solution? Mithun, can you explain me why are we saying that tincture of iodine is a homogeneous mixture, or why are we saying it's a solution?
Because the thing is they are not same, and
Huh? They're
they are
not
not
same
same.
as in?
What man?
Why are they not same as in? What are you trying to say here? That they are not same? I did not get that.
Because they both are pure substances,
Mm-hmm. No, my
and
point is, we have understood why are they mixtures. My point is, why are they homogeneous mixtures?
because they can dissolve in their I mean the salt can dissolve in alcohol.
Solute. Here salt is not present. Here is the element that is iodine. Fine. The solute
Okay.
can dissolve in the solvent here, which is alcohol. Wonderful. Good. And secondly, because of this dissolving, the composition will be uniform. There will be even distribution throughout the mixture. Fine. Aerated drinks. What do we mean by aerated drinks? Simple, that we are mixing any gaseous solute in the liquid drinks. What are cold drinks? It has a liquid which has been infused with carbon dioxide, which is gaseous. Therefore, they are called as aerated. Clear? So they are also, what are they? Can that be called as true solution? Can cold drinks be referred to as true solution?
Yes, ma'am.
No,
Yes. Dima, why no?
because
But
it
what
was
are true
mixed.
solutions? What are true solutions? There are solutions which are homogeneous. Yes, mixtures which are homogeneous, those are true solutions.
Yes.
They are homogeneous because they are uniform composition, evenly distributed, right?
Yes. Yes.
So when you have a cold drink, is there any part where it's most of the carbon dioxide, and when there's one
No.
part
No.
where there's no? Yeah. Understood? Fine. So
Yes.
we have discussed the air, 78% of nitrogen, therefore this acts as a solvent. All others are solutes here. Fine. Come to the properties of the solution. Homogeneous mixture, what is the size here? Particles less than 1 nanometer. Smaller than 1 nanometer. 1 nanometer is equal to 10 raised to the power minus 9 meters. Fine. Because of very small, they do not scatter the beam. They do not show Tyndall effect. Fine. Cannot be separated from the mixture by the process of filtration because they are stable. See, if the solution is stable, that means they're not getting separated into the components. Okay. Can we separate them using filtration? No. When does filtration actually work? When we are having two separate components and one is able to be like filtered and the other is left over there. Clear? So whenever the mixture is stable, filtration is not possible. Whenever the mixture is stable, the filtration is
Not possible.
not possible. Fine. Now tell me, do you know the concentration of a solution? Any idea regarding this topic? Both of you, but to say yes.
Yeah, yeah, ma'am.
You be, no, I'll discuss this in detail then.
Yeah, we have our teacher taught that about us.
Fine.
About
Do you
that.
mind, Mithun, you tell me what is the confusion there in this topic? Then I'll discuss that specifically. Then we'll move on to the
There's
suspensions
no
and cold.
confusion.
No confusion, Dima? Very quickly.
No.
One question, Machu, very quickly.
Yes, ma'am.
Total mass of solution. Okay. 120 grams. Yeah. Solvent is equal to 75%, okay, of the solution. Tell me the mass by mass concentration very quickly. Mass by mass concentration very quickly. What's the information given here? We have the total mass of the solution and we have the percentage of the solvent. Clear? Try very quickly, very quickly. See, the best approach to this, I'm solving it here.
And we have
Just
to
learn how
find
to solve.
the
Mass by mass, yes. Learn it
Yes,
very
sir.
quickly. See,
You have to find the
What is
mass
the
of solution, right?
mass of the solute, beta? We'll find the mass of the solute. That's what I'm telling. See, listen. Here, what should be the approach? First, know the formula for this. That is mass by mass conservation. We have to have the mass of solute. Yes. What should be the unit here? Divided by the mass of solution. What should be the unit in both the cases? Should that be gram? Into 100%. Mithun, just look here for a second and then you can solve it. Okay. This is the formula. We have the mass of the solution. What do we need? We need the mass of the solute. Clear? So first, from the given information, we will find the mass of the solute. Okay. Mass of the solute. What is given to us? Percentage of the solvent, right? If the percentage, the total percentage always has to be 100, right? So the percentage of solvent is 75%. Can I say the solute will be 25%? Yes or no? Yes or no? What's your response? Now, 25% of what? What is the total mass of the solution? See, mass of solute plus mass of
95%.
solvent will give you the mass of the solution, right? The total mass here is 120 grams. Out of that 120 grams, 25% is of the solute. Do you understand? Out of the total mass of the solution, 25% is of the solute. So therefore, 25 divided by 100 into 120 grams, I will get the mass of the solution. Let's consider that as x. Okay. Then, so it will be 1 by 4, 30 grams. 30 grams will be the mass of the solute. I will apply this in the formula 30 divided by 120 into 100%. Is it clear?
That is 25.
Sorry? Yeah, that will obviously eventually come out to be 25. I was just telling you the approach. Fine. If we have the percentage given, we will just take the total mass and we will get the mass of the solute. Fine. Simple method, you know, we have the mass of the solute, we have the mass of the solvent, we will add them together, we'll get the mass of the solution, we'll just calculate it. Fine. Any confusion in this? I'm moving on to suspensions, that is, I'm moving on to heterogeneous mixtures. Mithun, there seems to be some confusion on your face, beta. Please do let me know. Yes, Mithun.
I don't have any confusions now.
Okay, fine. What do we mean by heterogeneous mixtures? They are the mixtures, same, two or more than two pure substances mixed together, combined together in a variable composition, that is all there. But the mixture is not evenly distributed, right? The mixture is not evenly distributed. Now, when the mixture is not evenly distributed, the main reason is that because actual dissolving does not take place. Dissolving does not take place. And if the dissolvent does not take place, what is happening here? They are just suspended or dispersed in the solvent. The solvent is not the right term here, but I'm just trying to explain you. In one particle, in one substance, the particles of another substance are suspended or dispersed because they have not been dissolved. And why are they not dissolved? Because of the different particle sizes we will learn about. Fine. So the heterogeneous mixture is further of two types: suspension and colloidal solutions. Okay. Or the colloid. Fine. That is the difference here. See, it might be referred to as a colloidal solution. That is why we say that the solution, homogeneous solution, can also be referred to as a true solution. Then it would be very clear whether we are referring to a homogeneous solution or a heterogeneous solution. Colloidal solution, yes.
So, ma'am, sand and water is a heterogeneous mixture.
Yes, sand and water is for sure heterogeneous mixture. Yes. See, what I was saying is that, yes, if I am saying colloidal solution, I am referring to a solution that is heterogeneous in nature. If I am saying true solution, I am referring to a solution which is homogeneous in nature. Fine. Quickly coming to suspension beta. Properties of suspensions. First of all, they are heterogeneous. Okay, first of all, they are heterogeneous. Second, particle size, very important. I'm not writing every point here. We are short on time. Particle size more than, greater than 1000 nanometer. Is it understood? And when they have such large particle size, clearly the dissolving will not take place. Therefore, the particles in suspension are suspended or dispersed in the particles of another medium. Fine. Second, the particle size is quite greater. Therefore, they will scatter the light. Therefore, the path of the light will be visible. Therefore, they will show the Tyndall effect. Yes or no? Fine. The third, because the particle size is quite big, they are not dissolved. Therefore, if they have been left for some time undisturbed, they will be separated out into the components like this, as in the case of sand and water. Therefore, they are unstable. And if they are unstable, because they have been separated out into the components, they will be filtered through filtration. Is it understood? Yes or no?
Yes,
Okay.
ma'am.
One important point here, as soon as the mixture becomes unstable, let's say we mix sand and water, they have been mixed, okay, as of now we can say that they're mixed into each other, and then they're suspended into each other, fine. If they're left undisturbed for some time, they separate out into the components, sand is settled down at the bottom, water is there at the top. Then we cannot call that as a suspension because they have been separated out into the components. Then it cannot be called as a suspension. That is the only point, fine. The next point is there. They are unstable, so we have covered all the points here. Fine. Examples. Let's talk about the examples. Mud and water, sand and water,
Yeah.
chalk, powder and water. Okay. All of them are suspension. Fine. Mithun, any problem? Any point that you would want to discuss here? Fine. Moving on to colloid. What are colloids? They are again heterogeneous. Okay. Important point. They are heterogeneous, but seem to be or appear to be like homogeneous. Okay.
Yeah, ma'am.
Why? Because it appears that they have mixed properly, dissolving has taken place, but at the microscopic level, because of the difference in the particle size, mixing has not taken place, dissolving has not taken place. Is that clear? Fine.
Yes, ma'am.
What is the particle size here? It is between 1 to
1 to
1000
1000 grams. I mean
the
nanometers.
nanometer. Yeah, never use a unit. Okay, nanometer. Fine, no worries. So you see, it is between that of solution, true solution, and a suspension. Fine. The particles are big enough that the dissolving will not take place. They will also be suspended or dispersed. But the particles are big enough to scatter the light. Therefore,
Yes.
Tyndall effect will be shown. Fine. But the particles are not big enough for the solution to be unstable. Therefore, if the mixture is left undisturbed for some time, it will be a stable mixture because the components will not separate out. Therefore, no filtration here. Is it clear? Any confusion
Yes,
in this?
no, ma'am.
Fine. What are the examples here? Milk. Beta, you were talking about milk and water, right? Milk plus water is a colloidal solution. Fine.
They seem to be mixed, but they do not.
Yes. They have actually not dissolved into each other.
Ma'am, oil and water?
Oil and water, they're immiscible. They're immiscible liquid. No mixing. They will not even mix.
They're
Oil and
heterogeneous.
water, they're immiscible, right? We are talking about the liquids which are miscible. Because they are immiscible, they cannot be mixed. Oil and water, they will Mithun and Dima. Do you know the concept of miscible and immiscible liquid?
Yes,
ma'am.
I'm just asking.
Yeah, fine.
I
Hello.
was asking if in which it will come under, like colloidal solution or suspension.
Hello.
Yes, ma'am.
Just give me a second. I'm refreshing it. My network, I think, is having some issues. Just a second.
Okay, ma'am.
Hello. Is it better? Is it better now?
Yes, ma'am.
Yes, ma'am.
Okay, fine. Yes, Dima. Could you please repeat your question again? We were
I
discussing
was
about
asking,
miscible and immiscible. Yes.
yes, I was asking that I got the mixable and immixable, but oil and water it will come under suspension, right? Heterogeneous mixture suspension.
Okay. See, first of all, they will not be mixed. First point. Second, but if we actually mix it vigorously and properly, okay, they will be a suspension. And if left, as soon as we leave the mixing part, they will again separate out into two different layers. That is of oil and water because they are immiscible. I hope it answers your question. Yes. Second point here regarding the colloids, Bachu. In case of colloids, as was the case of two solutions, we have a solute and a solvent here. What is the solution?
Solvent. The solute is maybe the milk.
Yes. The phase and the medium. Okay,
Mhm.
the phase and the medium. See, quickly come to this point. The solute-like components of the dispersed particles in a colloid form the dispersed phase. Yes, and the dispersed medium, the dispersing medium is the one which acts like a solvent. Clear? So see here also the dispersed phase and the medium can have different states as we saw in the case of solution, right? The phase could be
Mhm.
solid, liquid, gaseous. The medium could be solid, liquid, and gaseous. Based on the combinations, we have different types of colloidal solutions. Are you getting it, Bachu? And these are the
Yes,
different
ma'am.
types of colloidal solutions. Fine. If the dispersed phase is liquid, the medium is gas, it is called as the aerosol. We have the examples, please go through it. Any confusion in this? Any confusion?
Mm.
No. One point here. I have a solution. Let's say I have a copper sulfate solution. Okay.
Yes.
What kind of a mixture is this? First of all, homogeneous or heterogeneous? And then
Heterogeneous.
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 Fine. In case of heterogeneous, what will you classify it as? And classify this one as?
Mm.
Suspension?
Suspension.
Colloid, I think colloid is a better one. It seems to be homogeneous, right?
Ma'am, I think it's suspension.
Suspension, yes. Fine. See, that's the point here. If you study this diagram carefully, A is the copper sulfate solution, okay, and B is the this thing. I think chalk solution or something like this, okay. Water and milk, water and milk, okay. The first one is not even showing the Tyndall effect. Therefore, it's
Yes.
a true solution. Therefore, it's a homogeneous mixture. From
Mhm.
this diagram itself, the questions could be, asked. What kind of a mixture is copper sulfate solution? It is a homogeneous mixture. It is not even showing the Tyndall effect. Is
Mhm.
that clear? Both of you?
Yes,
Fine.
ma'am.
Quickly draw this table if that's okay with you. I'm drawing it here just for the summary part.
Mhm.
Is it homogeneous? Is it heterogeneous?
Mhm.
It's also heterogeneous. Fine.
Hetero.
The next one, particle size,
1
less
to
than,
Or less than 1 nanometer.
yes. Okay. Greater than 1 nanometer, yes.
Yes.
Sorry,
1
1000
to
nanometer, yes, 1000 nanometer. In between 1 to 1000 nanometer. Fine. The next one, Tyndall effect.
No.
intellects does not occur.
Yes.
Yeah.
Shows Tyndall effect.
Yes.
Shows Tyndall effect. Fine. Next one, stable or unstable?
Stable.
Stable,
Stable.
Stable,
unstable,
unstable, and
unstable.
again stable. Okay.
Unstable.
Based on the stable and the unstable part, beta, can you tell me regarding the filtration? Will solution show filtration? No. Okay.
No.
Basically, can we separate the components of a solution using filtration? No, because it is a stable mixture. Fine. Can we separate the components of a suspension using filtration? Yes.
Yes.
Can we
Yes,
separate the
ma'am.
components of a? Sorry, beta.
Yeah, I said yes.
Yes. Fine. Can we separate the components of a colloid using filtration?
No.
Yes, ma'am.
Yes or no?
Yes.
Beta, it's a stable solution mixture. We cannot separate the components. Huh? Whenever the mixture is stable, we cannot separate the components using filtration. Other physical methods would be required, but not filtration. Is that okay, Mithun?
Yes, ma'am.
And one point regarding the mixtures here, please note this. We discussed that the mixtures are mixtures of two or more than two pure substances combined together in a variable composition. In a physical bonding, nature of bonding is physical, and since the bonding is physical, the separation methods are also physical methods. Whenever the mixtures are to be separated into the components, we need to have the physical methods of separation. Electrolysis is a chemical method of separation that cannot be applied here. But the next important point is that filtration is a type of physical method of separation. Therefore, in some of the mixtures, filtration cannot be applied because of the particle size and the property. Is it clear? We cannot say that the solution cannot be separated out using physical methods of separation. We are just saying that the solution cannot be separated out using filtration as a process. Is that okay?
Yes.
Both of you?
Yes.
Fine. So, Mithun, hopefully we have covered the syllabus for your exam tomorrow. Any confusion in here? Sandus, any confusion? Dima, any confusion, beta?
No, ma'am.
Do let me know what do you people want to study in the next class. Should we take the first half of the chapter, that is the pure substances, or should we move on to the third chapter? Whatever is your call. Please let me know.
No, I think we can go with the remaining chapter.
Yes,
The
ma'am. I also.
second half of the chapter, the pure substances.
Yes, ma'am.
For
Fine.
me also, ma'am. That's what
But-
I'm referring to.
Yes, Mithun.
Just a quick revision of the second half. That's it.
Yeah, because you have already attended some part of it in the other batch, right? So we'll try to finish it up as soon as possible.
Even we finished
Inside-
this chapter in school.
Fine. Dima, for you, do you want that in detail or you want that in a quick revision part?
I want a quick revision.
Why not? Also, we'll hopefully finish